Hello everyone, this is Dr. Mo Shiva, Professor of Electrical Engineering Department at California State University, Fullerton. Purpose of this video is to review Thevenin's and Norton's theorems. This is the second of the three examples that I do. If you have not seen the first video, please go ahead and review that video first. To do a brief review of the theorem, in a lot of applications we are interested in a part of the circuit, in this case RL, let's say, or it could be a network B, and we want to simplify the rest of the circuit. The complex network, boxed in red, can be simplified into a practical voltage source with open circuit voltage, or Thevenin, and Thevenin. That's Thevenin's equivalent. It could be simplified into a practical current source. Norton, I prefer short circuit, and Rn, which is same as RTh. From source transformation, we know V open circuit is Thevenin times I short circuit. The following table shows the recommended method for finding Thevenin's or Norton's equivalent circuit. Our first example, our first video was the first case. So in this video, we want to look at the case where we have all three types of elements: resistors, independent sources, and dependent sources. And the recommended method is to find short circuit current and open circuit voltage. Looking at the circuit, we have both types of sources. So we want to find V open circuit and short circuit current, and using those we can find Thevenin to be VOC over ISC. So let's try to find VOC. Assign polarity to the open circuit voltage. At XX, it's already open circuit voltage. Write the voltage drop going from top node to the bottom node. VOC is moving from the top X to the left. We see the positive terminal of the source, so 6 plus going straight down through the 40 ohm resistor in the direction of I1. We're using passive sign conventions, so V is equal to Ri, so 40 I. We see the positive of the next source, so plus 50 equal to 0. To find I1, let us write Kirchhoff's voltage law in this loop. So we have 40 I1 plus 50. Next, we see the dependent source, it's negative side, so minus voltage is 10 I1. And finally, 20 ohm resistor, current is I1 equal to 0. From our second equation, we find I1 equal to -1. Put that in the first equation. VOC is 56 plus 40 I1, so plus 40 times -1, we get 16 volts. What we need next is short circuit current. So looking at the circuit, short XX terminals, make sure you take short circuit current going down. Compared to VOC, we want to go from positive to negative, from top to bottom. So looking at the circuit, current here is ISC. Current on the top left portion from Kirchhoff's current law, we have I1 going down in the middle and I short circuit going to the right. So that's I1 plus ISC. We have the current everywhere. So let's write Kirchhoff's voltage law in the right mesh, starting at the lower left corner. So KVL applied to right mesh or right loop, whatever you want to call it. We have negative 50. Voltage across the 40 ohm resistor, we are going up, however, we are going against the direction of I1. So if you want to use I1, passive sign conventions, I1 should enter positive of that voltage. So we see the negative sign at the bottom and we are moving up. So write that as negative for the I1. And we see the negative 6 volt source on the top, nothing else, equal to 0. Apply Kirchhoff's voltage law to the outer loop. For starting at the lower left corner, first term is negative 10 I1. Current is I1 plus I short circuit, passing through the 20 ohms, plus 20 I1 plus ISC. And continue on the outer loop, we see negative side of the 6 volt source, so minus 6 equal to 0. Call this equation 1. And let's call this equation 2. From equation 1, we find I1. And it's equal to negative 1.4 amps. From equation 2, we have 10 I1 that's negative 10 plus 20, plus 20 I short circuit, minus 6 equal to 0. So that gives us I short circuit, ISC equal to 1/20th of 6 minus 10 I1. Substitute for that, negative 1.4, and we get 1 amp. So we have VOC and ISC. Thevenin's resistance is VOC divided by ISC. 16 over 1 gives us 16 ohms. So Thevenin's equivalent of the circuit is a practical voltage source with voltage VOC equal to 16, and Thevenin's resistance of 16 ohms, and that's the Thevenin's equivalent at XX terminals. If you had a load or another network B that was connected to this, we can put it back and use the simplified circuit. The third possible case for Thevenin's equivalent is having only dependent sources and resistors, and that will be the subject of the next video. Please watch that. Thank you.